Hey guys, welcome to the second video of 2.3 differentiation rules for products, quotients, secants, and tangents. So this is what we did in the last video. So now let me just restate what we're going to be doing today. So in the last video we did products. In this video we're going to be doing quotients. So let's go ahead and go down to our second part of the worksheet. Now, like in the last video, I'm going to give you guys a quick misconception of what students would do. Mistakes that students would do. So let's just say I have a function f of x is equal to, I don't know, sine x over 2x. And when they wanted to find the derivative of sine x over 2x, they took the derivative of the top, which is cosine, and they took the derivative of the bottom, which is 2. And that is incorrect. That's one big misconception. There's a special rule for taking derivative of quotients or fractions. Now, what they did here is they took the quotient of the derivatives. So the derivative of a quotient is not the quotient of derivatives. There's a special rule for that. And I'm going to go ahead and talk about that right now. So, quotient rule. When you want to take the derivative of a quotient or a fraction, the derivative of the quotient rule is the denominator times the derivative of the numerator minus the numerator, no prime, times the derivative of the denominator, all over denominator squared. Okay? Now that's the whole denominator squared, not just the x, the whole thing squared. Now let me go ahead and just re-explain this rule and restate this rule using u and v. So anytime we want to take the derivative of a u over v, it's simply the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. That should be much more easier to read and see. Now, notice, what is the similarities of the quotient rule versus the product rule? So let me write the product rule right here. The similarities that these two rules have in common is at the top of this quotient rule and the product rule, they both have interchanging derivatives and functions, except the difference is that one's a plus, one's a minus. And obviously there's a quotient, there's a fraction in the quotient rule. So that's one thing to help you guys out when you guys are doing these derivatives and memorizing these derivative rules, is that they kind of have the same thing when it comes to the mixture of the functions, except that one's minus and one's plus, and of course the other one has a fraction. So let's go ahead and use the product rule. So this is my u, this is my v. Y is equal to sine x over x cubed. This does not equal cosine x over 3x squared. No. Okay? So I want you guys to remove that misconception already from your head. The derivative of sine x over x cubed. So it's going to be v times, or let me use parentheses, times the derivative of sine x, which is the top, minus u times the derivative of v, all over v squared. So let me clean this up a little bit. Actually, let me choose a more finer pen. So, oh well, So what is x cubed times cosine x? X cubed times cosine x is not cosine x to the fourth. No. Okay? Cosine x is a term all by itself. It's simply just x cubed cosine x. That's it. You can't combine anything here. And then we have minus sine x times 3x squared. So it's going to be minus 3x squared times sine x all over. Well, let me do this over here in the top right. X cubed squared is the same thing as x cubed times x cubed, which is x to the 6. Or you can just multiply the powers and it's just x to the 6. That you should have learned already in algebra 2 and pre-cal. So it's x to the 6. So this is simply my answer. That is my derivative. Now, you could go further, and I suggest that you guys do go further only if you guys are capable of, because in the multiple choice AP exam, they're going to have an answer choice where they're reduced. What I mean by reduced is that if you notice, that's x to the 6, that's an x squared over x to the, x to the third, x squared, and x to the 6. That means that I can actually rewrite this as x cosine x minus 3 sine x all over x to the fourth. What just happened? Notice that that I had a common factor of x squared. I can take out x squared from the top and from the bottom and then cancel them out, which only leaves me with 1x here, no x, and x to the fourth. Example number 2. Let me go ahead and just remove some of this up here. Example number 2. Now we have the same thing. We have a quotient rule. So it's going to be u v. So it's going to be, this is the way I like to say it. So I'm sorry if I confuse you guys, but I always like to say the bottom times the derivative of the top. You know what? Before we do that, I noticed something here. That fourth root can be rewritten as x to the 1 over 4. So let's continue. So it's the bottom times the derivative of the top. The derivative of the top is 2x plus, no, not plus, minus the top times the derivative of the bottom. What is the derivative of x to the 1/4? Well, that is 1/4 x. Take 1 away from the power, and that is negative 3/4 power all over the bottom squared. Okay, this is an ugly problem, but you know what? It's a problem that's most likely going to be asked in the AP exam. If they ask you guys a problem using the quotient rule, it's probably going to involve trig or radical functions. Not going to be easy problems like the way we just did in the other examples. So let's go ahead and clean this up. It's going to be 2x to the 1/4 times x. I'm going to put a pretend 1 up here, minus x squared plus 2. Let me bring the 1/4 up here to the front. 1/4, and then x to the negative 3/4. All over, well, what is x to the 1/4 squared? You multiply the exponents, and you simply get x to the 1/2. Okay, so let me see how much time I have left, and I'm gonna go ahead and just stop it right here. You could, I want to challenge you guys to cleaning this up further. This is your answer. This is that is an acceptable answer in the AP exam if it was an open response, but if it was a multiple choice, you would have to choose the one that is equivalent to this expression. So I challenge you guys to do this.